The universe is not silent, but sings with the vibrations of space-time itself. This is the cutting edge of physics, where the geometry of reality might be composed of intricate waves. We will explore the profound idea that space-time has a sound, and listening to it could completely reshape our understanding of the cosmos. You will learn how these cosmic ripples reveal the hidden architecture of everything from black holes to the Big Bang itself. What if the force of gravity is actually a melody we are only beginning to hear? How could the echoes of colliding stars prove the existence of hidden dimensions? By the end, you will perceive the universe not as a static picture, but as a dynamic, resonant symphony. What does it mean to truly listen to the song of the cosmos? A trampoline's surface, stretched taut and then dramatically warped by a heavy weight, gives us a glimpse into the very nature of reality. This flexible fabric is Einstein's spacetime, a four-dimensional union where the three dimensions of space are inseparably woven with the dimension of time. Before Einstein, we thought of space as a static, empty stage and time as a universal clock ticking independently in the background. Matter simply moved across this rigid stage according to set rules. But Einstein revealed something far more beautiful and strange. He showed that mass and energy do not just sit on the stage, they actively reshape it. A star, a planet, any concentration of mass, creates a depression in this cosmic fabric, much like that bowling ball on the trampoline. The resulting curvature is not just a shape, it is a command. It dictates the paths that other objects will follow, a phenomenon we have always called gravity. An orbiting moon is not being pulled by a mysterious force, it is simply following the natural curve created by its planet. This was a revolutionary shift from a universe of absolute emptiness to a universe of dynamic geometry. The cosmos is not a fixed backdrop, but a responsive, living entity that bends and flexes with every movement of matter. It breathes with the orbits of planets and sighs with the spin of galaxies. And just like any flexible material, when it is disturbed, it does not simply warp and stay still. It ripples. These ripples are the subtle vibrations that carry the echoes of the most violent events across the universe, a direct consequence of spacetime's dynamic and malleable nature. Einstein's mathematics sang a song that no instrument of his time could hear. The equations of general relativity contained a hidden melody, a prediction of waves that were not made of water or sound, but of pure geometry. These gravitational waves are not ripples moving through spacetime. They are ripples made of spacetime itself, traveling outward at the ultimate speed limit, the speed of light. Think of the universe not as a still pond, but as a vast, elastic membrane. When a violent event occurs, it is like a sudden impact on that membrane. The fabric does not just dent, it oscillates, sending out concentric rings of distortion. As these waves pass through everything in their path, they perform a strange dance, alternately stretching space in one direction while squeezing it in the perpendicular direction. An object caught in this wave would not feel a push or a pull, but would itself be subtly deformed, becoming slightly longer and then slightly thinner, over and over again. Einstein, the architect of this incredible idea, doubted it could ever be confirmed. The distortions he calculated were so incredibly tiny, a fraction of the width of a proton over a distance of several kilometers, that detecting them seemed like a fantasy. He believed the universe's most dramatic events would only produce the faintest whispers by the time they reached us. But his theory was unequivocal: colossal cosmic disasters. The merging of black holes millions of times the mass of our Sun, the final death spiral of neutron stars, would shake the very foundations of reality, generating tremors that would ripple across billions of light years. This prediction ignited a scientific quest that would last for a full century, a hunt for the most elusive signal ever imagined. The challenge was to build an ear sensitive enough to listen to the stretching of space itself. The hunt for these whispers required an instrument of almost impossible sensitivity. The solution was not a single telescope, but a pair of them, separated by thousands of miles across the United States. These are the Laser Interferometer Gravitational Wave Observatories, known as LIGO. Each facility is an engineering marvel, a cathedral dedicated to silence. Its core is a monumental L-shaped structure, with two vacuum tubes, each 4 kilometers long, stretching out into the distance. Inside these tubes, laser beams race back and forth, bouncing between mirrors suspended with such precision that they are isolated from the constant rumble of the Earth itself. The entire system is designed to measure one thing: a change in distance. It compares the length of the two arms with a fidelity that is almost incomprehensible. LIGO can detect a shift smaller than 1/10,000th the diameter of a proton. To grasp that scale, it is like measuring the distance to our nearest star, Proxima Centauri, and noticing a change in that distance equal to the width of a single human hair. For decades, these instruments listened and heard only the quiet hum of our planet. The challenge was not just building a sensitive machine, but learning to distinguish a cosmic signal from an endless sea of noise, from the vibrations of a distant truck to the subtle tremors of an earthquake on the other side of the world. Then, on September 14, 2015, a whisper finally broke through the silence. A gravitational wave, generated by the cataclysmic merger of two black holes over 1 billion light-years away, washed over the Earth. It first reached the observatory in Louisiana, and then, just 7/1000ths of a second later, it was detected in Washington state. That tiny delay, the time it took for the ripple to travel between the two sites, confirmed its extraterrestrial origin. The signal was a perfect match for Einstein's predictions, a rapid crescendo ending in a final, decisive thud. When converted into sound, it was a simple chirp, a cosmic glissando that lasted less than half a second. But in that fleeting moment, a century-old prophecy was fulfilled. Humanity had directly detected a vibration of spacetime itself. We were no longer just stargazers, we had become listeners. This single chirp opened an entirely new window on the universe, one that does not rely on light. We can now hear events that are completely dark to telescopes: the final violent dance of black holes, the immense collisions of neutron stars. The silent universe had suddenly begun to sing, and its song was filled with violence and beauty we never knew existed. That brief chirp was a cosmic story compressed into a fifth of a second. Its rising pitch and swelling intensity were not random noise, but a precise translation of a gravitational catastrophe. The sound traced the final, frantic moments of two black holes locked in a death spiral. Each orbit brought them closer, their immense speeds warping spacetime with ever greater ferocity. The energy they radiated away in these gravitational waves was not insignificant. It was stolen directly from their orbital motion, tightening their spiral and sealing their fate. In the last milliseconds, as they merged into a single, more massive black hole, the event unleashed a staggering burst of power. For an instant, the gravitational wave output surpassed the combined light of every single star in the observable universe. Then, silence as the new black hole settled down, its surface quivering like a struck bell. The beauty of this signal was its informational purity. By reading the unique waveform of the chirp, scientists could decode the event's secrets. They calculated that the original black holes were each roughly 30 times the mass of our Sun, and that this monumental collision occurred an astonishing 1.3 billion light-years away. This was the true breakthrough. We were no longer just detecting a wave. We were using it to measure the properties of objects that emit no light whatsoever. The dark universe, once a realm of pure theory, had suddenly become audible. That first chirp was a proof of concept for an entirely new sense, confirming that binary black hole systems are not just theoretical possibilities but common realities in the cosmos. It was the opening note in a symphony we are only beginning to hear, raising an exciting question. If this was the sound of two black holes, what other instruments are waiting in the cosmic orchestra? But the orchestra of the cosmos is far more diverse than just black holes. In August of 2017, the listening posts of LIGO and its European partner, Virgo, detected a new kind of cosmic vibration. This signal was different. It lasted for nearly 100 seconds, a long, drawn-out crescendo compared to the black hole's brief chirp. It was the sound of two neutron stars, the impossibly dense cores of dead stars, locked in a final, fatal dance. This event, however, did not remain a secret heard only by gravitational wave detectors. Just 1.7 seconds after the gravitational signal peaked, space-based observatories detected an immense flash of gamma rays, the most powerful form of light. The universe had not only spoken, it had also flashed a bright, unmistakable beacon. For the first time, we had witnessed a cosmic cataclysm with two senses simultaneously. We heard the ripples in spacetime, and we saw the brilliant light it produced. This coordinated effort marked the dawn of multi-messenger astronomy, a new era where we perceive the universe through different channels of information, much like understanding a storm by seeing the lightning and hearing the thunder. The gravitational waves told a precise story of the neutron stars' masses and their final, frantic orbits as they spiraled inward and merged. The light that followed, observed by telescopes across the globe from radio waves to X-rays, revealed the explosive aftermath. It showed us the fiery kilonova, a forge of cosmic proportions where the heaviest elements in the universe were created. In that colossal explosion, atoms of gold, platinum, and other precious metals were forged and scattered into space. The very gold in a wedding ring or the platinum in a catalytic converter was likely born in such a violent merger billions of years ago. By combining the sound of the event with its light, astronomers could pinpoint the galaxy where it occurred and study the physics in unprecedented detail. This was not just confirmation, it was enrichment. Listening to spacetime provided the context for what we were seeing, turning a flash in the dark into a complete narrative of creation and destruction. The universe was no longer just singing, it was putting on a full sensory spectacle, revealing that its most energetic processes are best understood when we learn to both see and listen. That faint chirp is not a sound in the air, but a vibration etched into reality itself. When we assign a sound to a gravitational wave, we are translating a purely geometric phenomenon into something our brains can comprehend. These are not pressure waves moving through a medium like air. They are literal distortions in the fabric of spacetime. Imagine the space you occupy right now as a flexible grid. As a gravitational wave passes through, it does not push you, it reshapes the grid around you. The wave rhythmically stretches space along one axis while simultaneously compressing it along the other. If you were floating in the pristine vacuum near the LIGO detector during a strong event, your own body would experience this distortion. You would become infinitesimally taller and thinner, then moments later, slightly shorter and wider, all while the wave cycles through. You would not feel a thing, as every atom in your body and the ruler you might hold would be stretched and squeezed in perfect unison. This is the true nature of the sound we are hearing. Scientists take the frequency of this physical oscillation, the rate at which space is stretching and squeezing, and shift it up into the range of human hearing. A slow, steady vibration becomes a low hum, while an incredibly fast, accelerating oscillation becomes that iconic rising chirp. Each cosmic event has its own unique fingerprint. A pair of white dwarf stars orbiting each other for millions of years would produce an almost pure, monochromatic hum, a single sustained note in the cosmos. In contrast, the violent merger of two black holes creates a rapid, rising glissando that climaxes in a final thud. By listening to the precise character of these vibrations, we are conducting the most extreme tests of Einstein's theory of gravity. We are probing regions where gravity is so intense that it warps space to its absolute limit. Each ripple is a messenger, carrying encoded information about the violent events that created it, written in the language of geometry. Each ripple carries a hidden signature of the geometry it has traversed. While Einstein described a universe of smooth, continuous curves, the detection of gravitational waves offers a way to test if this elegant picture holds true under the most extreme scrutiny. Some of the most advanced theories in physics, particularly those attempting to unite gravity with quantum mechanics, propose a radically different vision for the fabric of reality. They suggest that at the tiniest conceivable scales, far smaller than a proton, spacetime might not be smooth at all. Instead, it could possess a frothy, granular texture, often called spacetime foam. This would be the fundamental grain of the universe, a turbulent sea of uncertainty at the quantum level. If this foam exists, it would leave a subtle mark on a gravitational wave traveling across billions of light years. Just as light passing through a frosted glass window gets slightly blurred and scattered, a gravitational wave interacting with this quantum foam would have its pristine signal subtly distorted. The wave would not arrive as a perfectly clean chirp, but perhaps with a faint fuzziness imprinted upon it. Our current detectors are not sensitive to these minuscule effects, but the next generation of observatories, both on Earth and in space, will listen with such incredible precision that they might finally hear this texture. They will be searching for the cosmic equivalent of a whisper that has traveled through a fine mist, its edges softened by the journey. This is not just about confirming a theory, it is about feeling the grain of the cosmos for the first time. The very act of listening could reveal whether the universe is built on a foundation of smooth marble or a complex, foamy quantum wood. Beyond texture, the shape of these waves, their polarization, holds even grander secrets. Just as light waves can be polarized, vibrating in a specific plane, so too can gravitational waves. In Einstein's universe, gravitational waves have only two possible polarizations, a plus shape and a cross shape, corresponding to the two ways they stretch and squeeze space. However, theories that propose extra dimensions, like string theory, predict additional, exotic polarizations. These would be vibrations that warp spacetime in ways that are impossible within the confines of our familiar four dimensions. Detecting such a signal would be like hearing an instrument play a note that should not exist in our orchestra, a clear sign of a reality with more spatial dimensions than the three we experience. Each gravitational wave event is therefore a direct probe into the deepest architecture of the cosmos. By analyzing the purity and pattern of these vibrations, we are not just listening to cosmic collisions, we are conducting an experiment on the fundamental geometry of the universe itself. The data streaming in from these dark events is a coded message about the nature of spacetime, potentially revealing a reality far more intricate and multidimensional than Einstein ever dreamed. The most ancient sounds of spacetime were born from the universe's first violent breath. Long before black holes collided, the cosmos itself rang like a bell struck with unimaginable force. This was the Big Bang, an event so colossal it set the entire fabric of reality vibrating. We cannot yet hear those original gravitational waves, but we have learned to see their ghostly echo. That echo is the cosmic microwave background, a faint glow of radiation that permeates all of space. It is the cooled remnant of the universe's fiery infancy, a baby picture taken when the cosmos was just 380,000 years old. Within this ancient light, physicists hunt for a specific pattern, a subtle swirl in its polarization known as B modes. This pattern is not caused by intervening matter or dust. It is theorized to be a fossil imprint, a scar left by primordial gravitational waves that rippled through the infant universe. These waves would have been generated during a mysterious epoch called inflation, a fraction of a second after the beginning when the universe is thought to have expanded at an exponential rate. This sudden, violent stretching of spacetime would have been powerful enough to create gravitational waves of immense amplitude. As these waves pass through the hot, dense plasma of the early universe, they would have subtly twisted the polarization of the light, leaving a unique signature for us to find. Detecting this signature is like finding the original soundtrack to the Big Bang. It would be a direct glimpse into a time when the universe was a trillionth of a second old. An era where the energy was so high that the forces of nature, including gravity, were likely unified. This search connects the vast, cosmic scales we observe today with the infinitesimal realm of quantum physics. Finding the imprint of these primordial waves would not only confirm the theory of inflation, but would also tell us about the energy at which quantum gravity began to shape our reality. It is the ultimate goal of listening to spacetime, to hear the faint whisper of creation itself, and finally understand the first note in the cosmic symphony. Our current detectors have given us the first few notes of a melody, but the full symphony remains a distant roar. These instruments are like holding a seashell to your ear, catching the loudest, most violent crashes from the cosmic shore, while a universe of subtler vibrations washes by unheard. The next generation of observatories is being designed to open this auditory range to its full extent, transforming our hearing from a whisper to a chorus. One of the most ambitious projects is the Laser Interferometer Space Antenna, or LISA. Instead of building its arms on the noisy surface of Earth, LISA will operate in the pristine quiet of space. It will consist of 3 separate spacecraft, flying in a perfect triangular formation millions of kilometers apart, connected by laser beams. This creates a gravitational wave detector of staggering scale, with an effective arm length far greater than the diameter of our entire planet. Freed from the constant rumbling of earthquakes and human activity, LISA will be tuned to hear the low frequencies of the cosmos. It will listen for the deep bass notes generated by events that are simply too slow and massive for Earth-based detectors to perceive. Imagine the supermassive black holes that lurk at the hearts of galaxies, each weighing millions or even billions of times the mass of our Sun. When 2 galaxies collide, these colossal black holes begin a gravitational dance, orbiting each other for millions of years before they finally merge. This majestic spiral produces a gravitational wave that is not a brief chirp, but a continuous, low-frequency tone that can last for years. LISA will be able to hear this song from the earliest epochs of the universe, tracing the growth of galaxies through the mergers of their dark hearts. At the same time, another method is already listening to an even deeper hum. Pulsar timing arrays use nature's own precision clocks, rapidly spinning neutron stars called pulsars. These cosmic lighthouses emit beams of radio waves with a regularity that rivals atomic clocks. As a gravitational wave passes through our region of the galaxy, it minutely distorts the spacetime between us and these pulsars, causing their ticks to arrive a fraction of a second early or late. By monitoring a network of these pulsars across the sky, astronomers are listening for a consistent pattern of distortions, a background hum created by the combined signal of every pair of supermassive black holes merging throughout the entire universe. This is the sound of cosmic history itself, the steady gravitational murmur of galaxy construction over billions of years. Together, these new ears will turn the universe from a place of occasional, startling noise into a resonant chamber of continuous sound. We will move from hearing individual chirps to discerning a complex gravitational soundtrack, where every frequency tells a different chapter of the story. This expansion of our senses promises to unveil a cosmic narrative far richer and more complex than anything we have yet imagined. This journey into the vibrational nature of reality leads us to a cliff edge overlooking a truly radical idea. What if the geometry of the universe, the very stage upon which everything plays out, is not the deepest level of reality? Some of the most profound theories in physics now suggest that space-time and its vibrations might be a projection, a cosmic illusion emerging from a far simpler, flatter reality. This is the holographic principle. It draws inspiration from a strange property of black holes. When an object falls into a black hole, it seems its information is lost forever, which violates a core tenet of quantum mechanics. Physicists discovered that the maximum amount of information a region of space can contain is not proportional to its volume, as you might expect, but to the surface area of its boundary. It is as if all the data needed to describe everything within a three-dimensional sphere. Every star, every planet, every person is somehow encoded on the two-dimensional surface of that sphere, like a cosmic DVD. The holographic principle takes this idea and applies it to the entire universe. In this view, our rich, three-dimensional experience of depth and distance could be a magnificent projection from a vast, two-dimensional surface at the edge of the cosmos. Think of a security hologram on a credit card. The flat, shiny surface contains all the information needed to generate a three-dimensional image that seems to float in space. Our universe might operate on a similar, unimaginably vast scale. If this is true, then what are the gravitational waves we have been listening to? They would not be ripples moving through a fundamental fabric, but rather the vibrational patterns on that distant, two-dimensional boundary, projected into the volume of our perceived reality. The stretching and squeezing of spacetime would be a secondary effect, a translation of a more fundamental vibration. This turns our understanding inside out. Sound and vibration are not phenomena happening within the universe. They could be the primary code from which the universe itself is built. The geometry we measure, from the curvature around a planet to the violent warps of colliding black holes, would be an emergent property, a consequence of complex vibrational interactions on a lower dimensional surface. While this remains a highly speculative frontier, it demonstrates the incredible power of listening to the cosmos. Each gravitational wave detection is not just an observation, it is a test of these deepest ideas. The quest to understand the sound of spacetime is pushing physics toward a potential theory of everything, a framework that could finally unite gravity with quantum mechanics. It forces us to question the very nature of what is real, asking if the solid, geometric universe we perceive is merely the grandest symphony ever composed, played on a surface we cannot yet see. This fundamental divide between the smooth curve of gravity and the quantum grain of matter is the final great puzzle of physics. On one hand, Einstein's general relativity paints a beautiful picture of a continuous, flexible spacetime that warps in response to mass and energy. On the other, quantum mechanics describes a chaotic, probabilistic world where particles pop in and out of existence and nothing is certain. These two theories are spectacularly successful in their own domains, but they become mathematically incompatible when pushed to the most extreme environments, like the singularity at the center of a black hole or the first moment of the Big Bang. To resolve this conflict, we need a theory of quantum gravity, a framework that describes the force of gravity using the rules of the quantum world. The gravitational waves we now detect are our most powerful probes into this mysterious frontier. They are the direct manifestation of gravity in its purest, most dynamic form. In a quantum theory of gravity, these ripples would not be purely geometric waves, but would themselves be composed of fundamental particles. Just as light is made of photons, gravity would be carried by hypothetical particles known as gravitons. A gravitational wave, in this view, would be a vast chorus of these massless gravitons traveling together through the cosmos. This idea presents a profound challenge because the graviton must mediate a force that is, inherently, the curvature of spacetime itself. Detecting a single graviton is currently far beyond our reach, as its interaction with matter is unimaginably weak. Yet, the collective behavior of countless gravitons in a wave might still reveal subtle clues. One of the most ambitious attempts to build this unified theory is string theory. It proposes a radical shift in our conception of reality's building blocks. Instead of point-like particles, the fundamental entities are unimaginably tiny, vibrating loops of energy or strings. The different vibrational patterns of these strings are what we perceive as different particles. One specific resonance, one particular note played on a string, would manifest as the graviton. In this elegant framework, the sound of spacetime is not just an analogy, it is a literal description of reality. The cosmos is a symphony of vibrating strings, and gravity is one of its deepest, most resonant tones. The geometry of the universe emerges from the complex interactions of these fundamental vibrations. When we listen to the chirp of merging black holes, we are, in a sense, hearing the collective music of an almost infinite number of these strings. The quest now is to find a signature, a tiny anomaly in the gravitational waves we detect, that cannot be explained by Einstein's classical theory alone. Perhaps at the very peak of a black hole merger, when spacetime is stretched to its absolute limit, a subtle fingerprint of this quantum granularity will be imprinted on the signal. Finding such a signature would be like hearing a slight distortion in a musical note that reveals the material the instrument is made from. It would be direct evidence that spacetime has a discrete quantum structure. This is the ultimate promise of listening to the cosmos, to move from observing the dance of gravity to understanding the very nature of the dancer. Each ripple from the dark universe carries not just a story of collision, but a coded message about the fundamental architecture of everything. The final, deafening crash of a black hole merger is not the end of the song. It is followed by a brief, pure tone, a fading hum that reveals the true nature of the new object left behind. This is the ringdown, the moment when the violently distorted black hole settles into its final, quiet state. Like a bell struck with immense force, it vibrates at specific, characteristic frequencies, emitting gravitational waves until the oscillations fade away. These vibrations are known as quasi-normal modes, and their pattern is exquisitely simple. The frequencies and the rate at which they decay depend on only two properties: the final black hole's mass and its spin. Nothing else matters. This simplicity makes the ringdown a powerful cosmic tuning fork. By carefully measuring the pitch and decay of this hum, scientists can directly weigh the black hole and measure how fast it is spinning. But the importance goes far beyond mere measurement. This sonic signature is a direct test of the cosmic rulebook written by Einstein. General relativity makes a very specific prediction about the kind of vibrations a black hole should produce. If the final object is a perfect, smooth black hole with an event horizon, its ringdown will match this prediction with mathematical precision. Any deviation from this expected tone would shatter our understanding. Imagine striking a bell and hearing a dull thud instead of a clear, ringing note. You would immediately suspect something was wrong with the bell itself. Similarly, if the ringdown signal contains unexpected overtones or decays too quickly, it could mean the object is not a true black hole. Perhaps it has a hard surface just outside where the horizon should be, causing the waves to reflect and alter the signal. Or maybe it is enveloped in a fuzzy, quantum haze, a structure predicted by some theories beyond Einstein's. Listening to the ringdown is like analyzing the unique timbre of a musical instrument to determine what it is made of. Is it a flawless crystal bell, or does it have an invisible crack? Each merger provides a new opportunity to check the blueprint of reality against the most extreme conditions nature can create. The music of black holes is not just a cosmic curiosity. It is the most stringent diagnostic tool we have for probing the ultimate fate of matter and the validity of our most fundamental laws. But the cosmic symphony may feature instruments far stranger than black holes. Beyond the violent collisions of massive objects, the early universe itself might have forged exotic structures capable of humming with gravitational energy. These are cosmic strings, theoretical filaments of pure energy thinner than a proton yet stretching across the entire cosmos. They are not made of matter, but are considered topological defects, flaws frozen into the very fabric of spacetime during its rapid cooling just after the Big Bang. Picture the universe undergoing a phase transition, much like water freezing into ice. As water freezes, its molecules align into a crystalline structure, but the process is not always perfect. Defects can form, places where the alignment is mismatched. Cosmic strings are the cosmic equivalent of these cracks, one-dimensional scars where the fundamental fields of the universe did not settle into their lowest energy state uniformly. If they exist, a single cosmic string could be as long as a galaxy cluster, possessing immense density and generating a powerful gravitational field around it. The truly fascinating part is how they would produce sound. These strings are under enormous tension, causing them to oscillate at velocities approaching the speed of light. As they whip through space, kinks and cusps can form on these vibrating filaments. A cusp is a point where the string doubles back on itself momentarily, reaching an incredible density. Such an event would be catastrophic for the geometry of spacetime, violently shaking it and releasing a sharp, powerful burst of gravitational waves. Unlike the clean chirp of a black hole merger, the signal from a cosmic string would be a sudden, percussive spike in the data. A network of strings throughout the universe would create a stochastic background, a cacophony of these sharp, random bursts overlapping with one another. Detecting this signal would be a direct window into the universe a fraction of a second after its birth, revealing the conditions of that primordial energy field. It would confirm a type of structure that interacts with the world only through gravity, casting no shadow and emitting no light. Finding cosmic strings would add a sharp, unpredictable rhythm to the gravitational wave symphony, a staccato beat from the deepest cracks in reality. Beyond the distinct chirps of individual collisions lies a far more subtle sound, a cosmic murmur that fills the entirety of space. This is the gravitational wave background, a persistent hum created not by one event, but by the overlapping echoes of countless cosmic catastrophes happening all across the universe, all the time. Think of it as the collective drone of a million distant waterfalls, each too far away to hear on its own, but together creating a constant, low rumble. The primary source of this hum is expected to be the combined gravitational waves from every pair of orbiting black holes and neutron stars that we cannot resolve individually. Across billions of galaxies, these binary systems are constantly spiraling inward, each emitting its own faint ripple. From our perspective, these waves arrive from every direction, overlapping and interfering with one another to create a stochastic, or random, signal that permeates the fabric of spacetime. It is the integrated sound of cosmic evolution, the gravitational residue of all the mergers that have ever occurred. But there may be an even more profound component to this hum, a signal from the very beginning of everything. Theorists suggest that the violent process of cosmic inflation, the Big Bang's initial explosive expansion, would have generated primordial gravitational waves of immense power. While their initial roar has faded over 13.8 billion years, their faint echo should still be present, superimposed onto the hum from astrophysical sources. Detecting this primordial whisper would be like hearing the faint, cooled breath of creation itself. To hear this background hum, we need a different kind of ear, one sensitive not to sharp chirps, but to a slow, persistent warping of space. This is the work of pulsar timing arrays. These projects use nature's most precise clocks, pulsars, which are rapidly spinning neutron stars that emit beams of radio waves with metronomic regularity. Astronomers carefully monitor the arrival times of these pulses from an array of pulsars scattered across our galaxy. As a gravitational wave from the background hum passes through the galaxy, it minutely distorts the spacetime between Earth and a pulsar, causing the pulse to arrive slightly early or late. No single pulsar's timing shift is conclusive, but by looking for a specific, correlated pattern of early and late arrivals across many pulsars, scientists can prove the presence of the hum. It is an incredibly delicate task, like trying to detect a gentle, planet-wide breeze by observing its minuscule effect on the swing of dozens of pendulums spread across a continent. Successfully measuring this gravitational background would open a new chapter in cosmology. It would provide a statistical census of the universe's population of binary black holes, telling us how common these dark partnerships are. More importantly, it would allow us to listen for that primordial signal, offering a direct glimpse into the universe's first moments and testing our theories of its explosive birth. This hum is the universe's baseline, the quiet but constant soundtrack against which all other cosmic dramas play out. Each ripple from a cosmic collision is a direct challenge to our understanding of gravity. For over a century, Einstein's theory of general relativity has withstood every experimental test thrown at it, from the bending of starlight to the precise orbits of planets. Yet, with every new gravitational wave we detect, we are conducting the most stringent examination imaginable. The signals recorded so far are a testament to the theory's power, matching the complex waveforms predicted by his equations with astonishing fidelity. The universe, it seems, is playing by Einstein's rules, but for many physicists, a perfect match is not the ultimate goal. They are actively searching for a tiny flaw. A minute discrepancy in the data would be far more exciting than another confirmation, because it would be a signpost pointing toward new physics. The properties of the waves themselves are under a microscope. Does the ripple always travel at exactly the speed of light, without even the slightest deviation? Some alternative theories suggest that different frequencies within a gravitational wave might travel at subtly different speeds, a phenomenon called dispersion. Imagine a beam of white light passing through a prism, where each color bends by a different amount. If gravitational waves exhibited a similar effect, it would mean that the high-frequency chirp at the end of a black hole merger might arrive at a slightly different time than the lower-frequency rumble that preceded it. Our current detectors have found no evidence for this, but as we listen to events from greater distances and with more sensitive instruments, we will be able to probe for these effects with ever greater precision. Another test involves the way gravity itself gravitates. In Einstein's theory, gravitational waves carry energy, and this energy should further curve the spacetime through which it travels. This creates subtle nonlinear effects that could slightly alter the wave's shape as it propagates across the universe. Detecting this self-interaction would be a spectacular validation of the theory's deepest intricacies. Finding a confirmed crack, however small, would be revolutionary. It would indicate that Einstein's breathtakingly beautiful geometric description of gravity is not the final word, but an incredibly accurate approximation of a deeper, more complete theory that unites gravity with the quantum world. The sound of spacetime is not just a new astronomical signal. It is the most precise tuning fork ever conceived, one that is now ringing across the cosmos, testing the very foundations of our reality. A black hole's shadow conceals a paradox that strikes at the heart of physics. Quantum mechanics, the rulebook for the subatomic world, contains a sacred law. Information can never be truly destroyed. If you burn a book, its ashes and smoke still contain, in principle, all the information needed to reconstruct every word, but a black hole presents a terrifying challenge. When something falls in, it passes the event horizon, the point of no return, and according to Einstein's general relativity, it is gone forever. Its information locked inside, inaccessible to the outside universe. Then Stephen Hawking added a devastating twist. He showed that black holes are not completely black. They slowly evaporate by emitting a faint glow of radiation. The problem is, this Hawking radiation appears to be purely random, carrying no information about what fell in. After eons, if the black hole evaporates completely, it seems all that information is irretrievably erased from reality, violating the core principle of quantum mechanics. This is the information paradox, a fundamental conflict between our two most powerful descriptions of nature. The gravitational waves we now detect offer a potential escape route. When two black holes spiral together, the ripples they produce carry a very specific kind of information: the final masses, spins, and orbital dynamics. According to classical physics, all other details, the identity of the stars that collapsed to form them, any planets or asteroids that fell in later, are permanently lost behind the new event horizon. Yet, if quantum gravity is correct, this information must be preserved. The key might be in the fine print of the gravitational wave signal. Perhaps during the violent merger and the subsequent ring-down, quantum effects leave a subtle imprint on the waves. The pristine tone of the ringing black hole might carry faint overtones, a complex harmonic structure that whispers the history of what formed it. It would be as if a bell, when struck, did not just ring with a pure note, but with a chorus of echoes that told the story of the ore it was smelted from. Detecting such a signature would mean that information is not lost, but rather encoded onto the event horizon itself, a concept known as the holographic principle, and then subtly broadcast into the universe through gravitational radiation. Listening to the precise sound of colliding black holes is no longer just astronomy. It is a direct experiment in fundamental physics. Each chirp is a test case for whether the universe allows information to vanish, or if every detail of its history is somehow preserved in the fabric of spacetime, waiting for us to learn how to listen. The paradox of information loss forces us to confront the limits of our cosmic hearing. But what if we could build a miniature universe in a laboratory, a place where we could directly manipulate the rules and listen to the results? Since we cannot create actual black holes on Earth, physicists have turned to a brilliant alternative: analog gravity. They construct systems where everyday phenomena, like flowing water or supercooled gases, behave in ways that are mathematically identical to the warping of spacetime. The most famous of these analogs is the sonic black hole, often called a dumb hole. Imagine a river flowing smoothly toward a waterfall. Now, imagine that the water accelerates so much as it approaches the edge that it flows faster than the speed of sound waves moving within it. Any sound wave trying to escape from near the waterfall would be dragged backward by the current, unable to make headway against the flow. This creates a sonic event horizon, a point of no return for sound, exactly analogous to the light-trapping horizon of a gravitational black hole. Researchers have created these conditions in the lab using superfluid helium or Bose-Einstein condensates, gases cooled to near absolute zero, where atoms move in unison like a single wave. By studying how sound waves behave near these artificial horizons, scientists can test ideas about how real gravitational waves might interact with a black hole's boundary. Most tantalizingly, these analog systems provide a potential way to detect a lab-made version of Hawking radiation. Stephen Hawking predicted that black holes should emit radiation due to quantum effects at the horizon. In a sonic black hole, the analog of this radiation would be a spontaneous emission of sound particles, or phonons, from the horizon. Detecting this faint whisper of sound in a controlled experiment would be a monumental step, offering indirect but powerful support for Hawking's revolutionary idea. These tabletop experiments are more than just clever tricks. They are bridges. They translate the abstract, four-dimensional geometry of general relativity into a tangible, three-dimensional fluid dynamics problem that we can see and measure. While the physics is not exactly the same, the mathematical parallels are so strong that insights gained in the lab can illuminate the behavior of the cosmos. We are learning to play the notes of spacetime on instruments we built ourselves, hearing echoes of the universe's deepest mysteries in the gentle flow of water and the collective hum of atoms. The very existence of gravitational waves as a detectable signal rests upon a cosmic tightrope walk. The fundamental constants of our universe, like the strength of gravity and the speed of light, appear to be perfectly balanced for this phenomenon to be observable. If gravity were significantly stronger, the ripples from a black hole merger might be more like tsunamis, but the universe would likely be a far more violent and unstable place, perhaps preventing the long-term existence of stars and planets. If it were much weaker, the vibrations might be so faint as to be completely imperceptible across cosmic distances. Even the number of spatial dimensions is critical. In a universe with more than 3 spatial dimensions, the force of gravity would diminish so rapidly with distance that the intricate, long-range waves we detect would simply not form. The clear, clean chirp that LIGO recorded is a direct consequence of our specific 3-dimensional reality. This delicate tuning forces a profound philosophical question. Is it a mere coincidence that we inhabit a cosmos where spacetime not only vibrates, but does so in a way we can ultimately measure? This line of thinking leads to the anthropic principle, a contentious but fascinating idea. It suggests that the observable universe must possess properties that allow for the emergence of conscious observers. We should not be surprised to find ourselves in a universe compatible with our existence. In this view, the sound of spacetime might be more than a curious feature. It could be a necessary ingredient. The propagation of gravitational waves is tied to the very fabric of geometry that allows for stable galaxies, long-lived stars, and planetary systems where complexity can arise. A universe silent in this particular way might also be a universe incapable of fostering life that can ask questions. Therefore, our ability to listen to the cosmos is not just a technological triumph, but perhaps a predictable outcome of a universe that is, in its deepest structure, resonant and knowable. The sound we hear might be the signature of a cosmos tuned not just for existence, but for understanding. Our detection of these waves is a physical act that completes a cosmic circuit. Before the laser light in LIGO arms measured an infinitesimal stretch and squeeze, the incoming gravitational wave existed as a cloud of potential, a superposition of states predicted by quantum theory. The moment the signal was registered, that cloud collapsed into a single, definitive history, the specific chirp we now analyze. This is not to say we caused the black holes to collide, but that our active observation fixed one specific story out of many possible variations. We transformed a fuzzy probability into a concrete day, a point etched into scientific record. The universe presented a question written in the language of geometry, and our instruments provided the answer, finalizing an event that occurred a billion years ago. This interplay suggests that the sound of spacetime is not a finished symphony playing in an empty hall. It is a duet between the cosmos and a conscious listener. By choosing to build these incredible ears, we are not passive recipients of a signal. We are active participants in crystallizing a facet of reality. The geometric universe we map through these vibrations is, in part, a universe revealed by our specific mode of questioning. Our listening shapes the reality we perceive, tuning our understanding to the specific frequencies we are equipped to hear. This connects the cold precision of physics to the warm mystery of perception, hinting that the deepest notes of the cosmos may only sound when there is someone there to hear them. The immense silence required to hear the cosmos has, paradoxically, given rise to a cascade of technological noise that echoes through our daily lives. Pushing the boundaries of measurement to such an extreme degree demanded not just a single invention, but a revolution across multiple fields of engineering. Consider the lasers at the heart of LIGO. To detect a shift smaller than a proton, the laser light itself must be phenomenally pure and stable, its wavelength consistent to an almost unimaginable degree. The quest for this perfection has dramatically advanced laser technology. leading to more powerful and precise instruments that are now finding uses in manufacturing, where they can measure the integrity of aircraft wings or machine parts with microscopic accuracy. Vibration isolation, the art of creating a quiet island in a seismically noisy world, has applications far beyond astrophysics. The techniques developed to suspend LIGO mirrors, insulating them from the rumble of distant trucks and ocean waves, are now informing the design of ultra-sensitive equipment. In medicine, this could lead to next-generation brain scanners that are immune to the vibrations of a hospital, producing clearer, more detailed images for diagnosis. Even the mirrors themselves are marvels of material science. Their coatings are among the most reflective ever created, losing fewer than 1 in a million photons. This kind of perfection in optical coatings is crucial for the high-powered lasers used in eye surgery and industrial cutting, making procedures safer and more effective. But perhaps the most surprising export from this cosmic listening post is the software. The challenge was not just collecting data, but understanding it. The raw signal from the detectors is a chaotic roar of environmental noise, and buried within it is the faintest of whispers. To find it, scientists had to create incredibly sophisticated algorithms, digital sieves capable of identifying a specific pattern of ripples. These same pattern recognition techniques are now being adapted to sift through other types of complex data. In finance, they can help model market fluctuations and identify subtle risks. In medicine, they are being used to analyze medical scans, spotting the earliest signs of diseases like cancer by recognizing patterns that are invisible to the human eye. The gravitational wave signal is a needle in a universe-sized haystack, and the tools we built to find it are now helping us find other needles, ones that can save lives and build stronger economies. This demonstrates a profound truth about fundamental science. The drive to answer a grand, seemingly abstract question about the nature of the cosmos consistently forces us to invent new ways of seeing, measuring, and thinking. These tools, born from curiosity, inevitably spill over into the wider world, transforming our technology and improving our lives in unpredictable but deeply meaningful ways. The sound of space-time, it turns out, is not just a message from the void, but a catalyst for innovation on Earth. Long before our lasers could measure the stretching of space, the human mind perceived a universe alive with vibration. Ancient sages and philosophers, separated by continents and millennia, arrived at a strikingly similar intuition, that reality is fundamentally sonic. In India, the principle of Nada Brahma declared the world is sound, a divine vibration emanating from the source of all creation. 1,000 years later and halfway across the world, the Greek mathematician Pythagoras listened to the simple ratios of a vibrating string and envisioned a celestial orchestra. He proposed that the planets in their perfect orbits produced a harmonic resonance, a music of the spheres inaudible to ordinary human ears. These were not scientific theories in the modern sense, but profound metaphysical insights. They recognized pattern, rhythm, and harmony as the underlying principles of an ordered cosmos, with sound serving as the most immediate metaphor for this invisible order. The common thread is the idea of vibration as a creative force, a fundamental frequency from which the complex tapestry of existence is woven. The gravitational waves we detect today are not a repudiation of this ancient wisdom, but its startling physical validation. That chirp from a billion light-years away is the literal music of the spheres, not as a metaphorical harmony, but as a measurable oscillation in the geometry of the planet's very stage. The Pythagorean dream of a cosmic symphony was a poetic premonition of the ripples in space-time we now record. This connection does not diminish the scientific achievement, it deepens it. It reveals that our drive to comprehend the universe often circles back to profound archetypal ideas. The difference now is that we are armed with the tools of rigorous inquiry. We have moved from contemplating the harmony of the heavens to listening to the specific notes played by colliding black holes. This bridges a divide that has existed for centuries, uniting the poetic imagination of the philosopher with the precise measurement of the physicist. Both are seeking the same fundamental truth, one through metaphor and introspection, the other through data and deduction. The Song of Spacetime is a reminder that our quest for understanding is a continuous story, where ancient intuition and modern discovery can resonate together, creating a richer, more complete harmony. This cosmic story is now a classroom. The narrative of detecting spacetime's ripples possesses a unique power to captivate minds far beyond the physics laboratory. It is a tale that blends high-stakes prediction with human perseverance, culminating in a discovery that feels almost like science fiction made real. The very idea of listening to a black hole collision that occurred when Earth was inhabited only by single-celled organisms makes the vast scales of the cosmos suddenly intimate and thrilling. For a student grappling with abstract mathematics, this story provides the ultimate payoff, demonstrating that equations scribbled on a chalkboard can predict the real-world soundtrack of a billion-year-old catastrophe. It transforms gravity from a simple force that makes things fall into a dynamic, vibrating fabric that can be measured and heard. This tangible connection between profound theory and observable reality is a potent antidote to the question of why we learn these difficult subjects in the first place. Educational programs are harnessing this power, creating planetarium shows where audiences don't just see the stars, but feel the bass note of a simulated black hole merger. Interactive exhibits allow students to manipulate virtual detectors, learning the principles of laser interferometry by trying to spot a simulated ripple in a sea of noise. These experiences make the geometry of spacetime a sensory adventure, not just a chapter in a textbook. The result is a new generation that sees science not as a collection of settled facts, but as an ongoing detective story. They are the future engineers who will design the next LIGO-like observatory in space, the mathematicians who will decode more complex waveforms, and the physicists who will ask the next questions that we cannot yet even formulate. The sound of spacetime is more than a signal. It is an invitation, a call to curiosity that resonates with the innate human desire to explore. It proves that the universe is not a silent, static picture, but a dynamic symphony waiting for ever more attentive ears. This profound new sense comes with a deep responsibility. The ability to listen to the cosmos is not the work of a single nation or a solitary genius, but a global chorus of thousands of scientists, engineers, and thinkers from dozens of countries. They share data openly, troubleshoot problems collectively, and celebrate discoveries as a unified human endeavor. In a world often divided, this stands as a remarkable testament to peaceful international cooperation, a shared project aimed solely at understanding our universe. The technology born from this quest, from the world's most stable lasers to unprecedented vibration isolation systems, raises its own ethical questions. While directly weaponizing a gravitational wave is a physical impossibility, the advanced sensing capabilities could have dual uses. The same precision that measures a spacetime ripple could, in theory, be adapted for enhanced surveillance or stealth technologies. This places a burden of stewardship upon the scientific community and society at large, to ensure that knowledge born from pure curiosity is guided by a moral compass. The primary ethical consideration, however, lies not in potential misuse, but in the positive application of this cosmic perspective. This knowledge holds the power to profoundly redefine our self-image. Hearing the collision of black holes reminds us that the forces shaping the cosmos are immense and impersonal, that our planet is a fragile stage adrift in a dynamic, often violent, arena. This can inspire a sense of planetary unity, a realization that all human conflict and aspiration occurs on a single, small world humming with the echoes of creation. The choice is ours. Will this grand new window onto the universe be used to foster greater wonder, to educate future generations, and to highlight our shared humanity? The story of listening to Spacetime is ultimately a story about the best of what we are capable of. Our ingenuity, our persistence, and our innate desire to comprehend the symphony of which we are a small, but now listening, part. Our journey through the sound of spacetime leaves us with a universe profoundly different from the silent, static expanse we once imagined. Every ripple confirms a cosmos that is dynamic, resonant, and deeply interconnected. From Einstein's hesitant prediction a century ago to the triumphant chirp that echoed through LIGO vacuum tubes, we have learned to listen to a gravitational symphony narrating the most violent and creative events across the ages. These vibrations are far more than mere signals. They are direct probes into the very geometry of reality, testing our most fundamental theories at their absolute limits. Each detection is a stringent experiment, challenging the smooth curves of general relativity against the potential grain of quantum foam and the possibility of hidden dimensions. This ongoing conversation between theory and observation guides us toward a deeper unity, a potential theory of everything that could finally reconcile the large and the small. The sound of spacetime forces a radical shift in perspective, inviting us to perceive reality not as a fixed stage, but as a living, breathing entity whose music we have only just begun to hear. As we construct ever more sensitive observatories, from space-based antennas to pulsar timing arrays, our listening skills will continue to refine. Who knows what other melodies await discovery in the cosmic static? What ancient rhythms from the dawn of time or percussive beats from exotic strings? The universe is not silent. It is speaking to us in a language of geometry and vibration. We have only to continue listening. What aspect of this cosmic sound amazes you the most? Share your thoughts in the comments, and subscribe to join us as we continue exploring the profound mysteries of the universe.